Welcome to our bioprocess engineering online tutorial on microbial fermentation simulation models. Through the bioprocess engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. Industrial fermentations employ a diverse range of microorganisms, including bacteria, yeast, and filamentous fungi, to produce valuable bioproducts on a large scale. These microorganisms are cultivated in fermenters that vary in capacity from small laboratory vessels to industrial units capable of holding several thousand cubic meters of culture. When microbial cells are cultivated in bioreactors containing nutrient-rich media, they consume essential substrates, such as sugars, nitrogen sources, and, in the case of aerobic fermentations, oxygen. These substrates are metabolized and transformed into microbial biomass, along with various fermentation products or metabolites. Throughout the fermentation process, the composition of the culture medium changes continuously. Typically, substrate concentrations decrease over time, while biomass and product levels increase. These fermentation dynamics, the time-dependent variations in substrate, biomass, and product concentrations, are strongly influenced by multiple factors, including the microbial strain, medium composition, and operating conditions within the fermenter. To accelerate process scale-up and optimization while reducing development costs, bioprocess engineers increasingly rely on simulation models. For fermentation processes, these models can predict the dynamic behavior of the system, capturing how a specific microbial transformation responds to the culture medium and fermenter operating conditions. In this tutorial, we will explore how to construct a simulation model of fermentation processes. You will learn how to integrate the kinetic laws governing microbial reactions, the thermodynamic and kinetic principles of oxygen transfer, and the mass balance equations for key fermentation components, to predict the time-dependent variations of substrates, microbial biomass, and metabolites throughout the course of a fermentation. The modeling methodology will be demonstrated through a case study on glutamic acid fermentation. In this process, a thermo-inducible strain of Corynebacterium glutamicum is employed, which excretes large amounts of glutamate in response to an increase in temperature. With these bacteria, the dynamics of batch fermentation exhibit distinct patterns. The sugar concentration steadily decreases throughout the entire fermentation. The dissolved oxygen concentration follows a more complex trajectory. It declines rapidly, reaches a minimum, and then rises again. The bacterial biomass concentration increases slowly at first, then more rapidly, before eventually reaching a stationary phase. The glutamate concentration begins to increase following the temperature shift. The suggested methodology for modeling microbial fermentations follows the following steps. 1. Formulate hypotheses regarding the fundamental phenomena governing the fermentation. 2. Select appropriate thermodynamic and kinetic laws to describe these phenomena, particularly those related to microbial growth kinetics and oxygen transfer. 3. Derive the model equations based on mass balance relationships for the key fermentation components. 4. Solve the resulting system of equations to simulate the fermentation dynamics. In fermenters, the time-dependent variations in the concentrations of fermentation components are governed by three fundamental phenomena: microbial conversion reactions, mass transfer, and fluid flow. The primary driver of these concentration changes is the microbial reaction, encompassing the rates at which cells consume substrates, grow, and produce metabolites. In addition, physical phenomena significantly influence the overall culture dynamics. Mass transfer, particularly the rates of oxygen uptake and carbon dioxide release between the gas phase and the liquid medium. Fluid flow, the circulation and mixing of the liquid phase within the fermenter. These phenomena are analyzed in greater detail in the tutorial Microbial Fermentation Governing Phenomena. After identifying the fundamental phenomena governing the fermentation, the next phase in constructing the simulation model involves deriving the mathematical relationships that describe the time-dependent variations in the concentrations of the different components. This modeling methodology follows the concept of the modeling triangle, which integrates material balance equations, representing the principle of mass conservation, with the thermodynamic and kinetic laws that describe the underlying physical and biochemical phenomena. In fermentation modeling, the most important relationships are those that describe the kinetic characteristics of the microbial cells used in the process. These kinetic laws predict the specific rates of microbial metabolism, typically expressed per gram of active cells as functions of environmental conditions. The key rates include the specific substrate consumption rate, QS, the specific growth rate, mu, and the specific rate of metabolite production, denoted as QM. These cellular rates depend on several environmental parameters that generally vary throughout the culture. Substrate and nutrient concentrations in the culture medium, particularly carbon sources and dissolved oxygen. Concentrations of excreted metabolites, which may inhibit or regulate microbial activity. Physicochemical variables, such as temperature and pH. The microbial kinetic laws must be adapted to reflect the characteristic growth pattern of the microorganism. As microorganisms consume nutrients, they typically progress through distinct growth phases. Lag phase, a period of little to no growth, during which cells adapt to the new environmental conditions. Exponential phase, characterized by rapid cell division and a sharp increase in biomass concentration. Deceleration phase, the growth rate begins to slow as nutrients become limited or inhibitory byproducts accumulate. Stationary phase, growth ceases and the population stabilizes due to nutrient depletion or other environmental constraints. To model fermentations that progress through consecutive phases, from lag to stationary, with associated metabolite production, as in glutamic acid fermentation, the most suitable approach is to employ physiological state models. These models distinguish between different cellular physiological states and describe the transitions that occur as cells shift between distinct metabolic modes during the course of fermentation. These physiological states typically include latent cells, recently inoculated cells, adapting to the new medium and environmental conditions, exhibiting minimal or no growth. Growing cells, characterized by active and rapid cell division, leading to biomass accumulation. Producing cells, in which metabolic activity is redirected toward the synthesis of the desired product, rather than continued cell growth. The transition from the growing to the producing state is often triggered by external factors, such as the addition of an inducer, a temperature shift, or nutrient limitation. The initial latency phase of fermentation is conceptualized by assuming that, initially, the inoculated cells reside in a latent state characterized by minimal substrates, consumption, and growth rate. These latent cells X-lat gradually transition into actively growing cells Xg. The transition rate, denoted as R-lat, measured in grams of cells per liter per hour, is assumed to be proportional to the concentration of latent cells X-lat, with K-lat representing the first-order transition rate constant. The value of K-lat determines the duration of the latency phase. A higher K-lat results in a shorter latency phase. A similar kinetic formulation is used to describe the physiological transition from growing cells Xg to producing cells Xp. The transition rate, denoted as RGP, expressed in grams of cells per liter per hour, is assumed to be proportional to the concentration of growing cells xg, with kgp representing the first-order transition rate constant. What are the kinetic laws describing the growing cells? Growing cells consume nutrients or substrates to produce new cellular biomass. Their growth is characterized by the specific growth rate mu, defined as the rate of cell mass formation, per unit of existing cell mass, typically expressed in grams of cells produced per gram of cells per hour. The specific growth rate is commonly described by a monad-type equation, which relates mu to the concentration of the limiting carbon source, in this case sugar. Mu equals mu max S over Ks plus S, where mu max is the maximum specific growth rate, and Ks is the half saturation constant, representing the sugar concentration at which the specific growth rate equals half of mu max. For growing cells, the most relevant substrate is the carbon source, typically sugar. The specific sugar consumption rate, QSG, of growing cells, expressed in grams of sugar consumed per gram of cells per hour, is generally assumed to be proportional to the specific growth rate mu, QSG, equals YS over X, mu, where YS over X is the stoichiometric coefficient, expressed in gram of substrate consumed per gram of biomass produced. In aerobic fermentations, the specific oxygen consumption rate of growing cells, QO2G, in gram of oxygen consumed per gram of cells per hour, is likewise considered proportional to the specific growth rate. QO2G equals YO2 over X, mu, where YO2 over X is the stoichiometric coefficient, expressed in grams of oxygen consumed per gram of biomass produced. What are the rate laws characterizing producing cells? Producing cells consume sugar and oxygen to synthesize metabolites under growth-arrested conditions. In the case of glutamate production by corynebacteria, the specific metabolite production rate, QM, is characterized by a maximum specific production rate, QM max, reduced by substrate limitation in product inhibition terms. QM equals QM max multiplied by S over Km plus S and by 1 minus M over M max, where S is the sugar concentration. Km is the half saturation constant for the sugar. M is the metabolite concentration, and M max is the maximum metabolite concentration, beyond which production is fully inhibited. For producing cells, the specific sugar consumption rate, QSP, is assumed to be proportional to the specific metabolite production rate, QM. QSP equals YS over M, QM, where YS over M is the stoichiometric coefficient, expressed in grams of sugar consumed per gram of metabolite produced. Similarly, the specific oxygen consumption rate of producing cells, QO2P, is also considered proportional to the specific metabolite production rate. QO2P equals YO2 over M, QM, where YO2 over M is the stoichiometric coefficient, in gram of oxygen consumed per gram of metabolite produced. In summary, for a microbial strain such as glutamate-excreting corynebacterium, the kinetic model includes 3 consecutive physiological states: latent, growing, and producing cells, transition rate laws describing the shifts between these states, growth and substrate consumption kinetics specific to the growing phase, and metabolite production and substrate consumption kinetics characteristic of the producing phase. The rate laws define specific rates either as functions of the medium composition or as relationships between different specific rates. Aerobic fermentations are continuously aerated to supply oxygen, essential for cellular metabolism, and to remove carbon dioxide. This constant gas exchange is necessary because of the low solubility of oxygen and carbon dioxide in aqueous culture media. The supply and consumption of oxygen in the fermenter occurs in 3 stages. First, oxygen is introduced into the fermenter through the inlet air system. Next, a portion of the oxygen transfers from the air phase into the liquid medium. Finally, the cells present in the medium consume the dissolved oxygen for metabolic activities. What is the thermodynamic law for oxygen solubility in water? Oxygen solubility refers to the concentration of dissolved oxygen in water at equilibrium with the oxygen partial pressure in the air. It represents the maximum amount of oxygen that can dissolve in water at a given temperature and atmospheric oxygen content. Oxygen solubility is described by Henry's law, which governs the equilibrium between oxygen and air and its dissolved form in water. The oxygen solubility, O2 star, expressed in gram oxygen per liter, is calculated as the partial pressure, PO2 in atmosphere, divided by the Henry's constant, KO2, in atmosphere liter per gram. The partial pressure, PO2 of oxygen in air, is the product of the oxygen molar fraction, YO2, by the total pressure. At 30 degrees Celsius and 1 atmosphere of air, the solubility of oxygen O2 star is near 8 milligrams per liter. What is the kinetic law for the oxygen transfer rate? Oxygen transfer between the air and the liquid medium is primarily limited by the transfer of oxygen from the first liquid layer at the air-liquid interface, which is saturated with oxygen, to the bulk liquid medium where the dissolved oxygen concentration is O2L. The rate of oxygen transfer, JO2, in grams of oxygen per hour is described by the following mass transfer law, accounting for diffusion and convection at the air-liquid interface. JO2 equals SKL, O2 star minus O2L, where S is the transfer surface area between the air and liquid solution in square meters. KL is the oxygen mass transfer coefficient in the liquid phase solution in meter per second. The oxygen concentration difference, O2 star minus O2L, serves as the driving force for the oxygen transfer. One generally introduces the volumetric interfacial surface area A in square meters per cubic meter between the air and the solution, defined as the transfer surface area S divided by the medium volume V. The rate of oxygen transfer, JO2, is then expressed as JO2 equals KLA, O2 star minus O2L, V. The product KLA, in our -1, is the volumetric oxygen transfer coefficient between the air and the liquid solution. It characterizes the oxygen transfer capacity of the aeration system. What governs the oxygen transfer capacity, KLA? The oxygen transfer coefficient, KLA, depends primarily on the fluid flow or agitation within the fermenter and on the aeration rate. 1. Influence of agitation. The first major factor affecting KLA is the medium agitation power, or mixing intensity. The mechanical power consumption for tank agitation, PA in watts, is typically estimated using the following relationship. PA equals NP, rho, n to the power 3, dA to the power 5, where NP is the impeller power number, rho is the fluid density in kilogram per cubic meter, n is the impeller rotational speed in second minus 1, and dA is the impeller diameter in meter. According to this relation, PA is directly proportional to the fluid density rho, increases with the cube of the impeller speed n, and increases with the fifth power of the impeller diameter dA. It is directly proportional to the power number NP, which depends on the impeller geometry. 2. Influence of aeration. The airflow rate QA introduced into the fermenter, typically in liters per minute, is another key determinant of KLA. More precisely, KLA depends on the gas superficial velocity UG in meter per second, defined as UG equals QA over omega, where omega is the cross-sectional area of the fermenter in square meters. Higher gas flow rates, and thus higher UG, enhance gas-liquid interfacial area and mixing, leading to improved oxygen transfer efficiency. In aerated fermenters, the increase in the volumetric oxygen transfer coefficient KLA with rising agitation power and airflow rate can be described by an empirical correlation of the form KLA equals A PAG over V to the power M UG to the power N, where PAG over V is the volumetric agitation power, UG is the gas superficial velocity, and A, M, and N are empirical constants that depend on the fermenter design and scale. Typical values for large-scale agitated fermenters are A equals 0.002, M equals 0.7, and N equals 0.3. In summary, the fermentation aeration process is modeled using the thermodynamic law of oxygen solubility and the kinetic law of oxygen transfer, in which the oxygen transfer coefficient KLA is correlated with the fermenter's agitation power and airflow rate. After formulating the laws governing the microbial cell kinetics and the oxygen transfer, the subsequent task involves establishing the differential equations that depict the temporal changes of the cells, substrates, and metabolite concentrations throughout the fermentation. These equations are derived by writing the instantaneous mass balances for the fermentation components. For a component, the instantaneous mass balance, that expresses the fundamental principle of mass conservation at each instant, involves four terms: the inlet rate, from the outside to the inside of the fermenter; the outlet rate, from the inside to the outside of the fermenter; the biotransformation rate, that can be a production rate for a product or a consumption rate for a substrate; and the internal variation rate, that represents the rate of the component's mass variation inside the fermenter. The instantaneous mass balance relation is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced biomass and metabolite, negative for the consumed substrates. For a batch fermentation, there are no inlet rate and outlet rate terms, and the instantaneous balance simplifies to plus or minus production rate equals variation rate. For the latent cells, the instantaneous balance, in gram cells per hour, on the fermenter writes minus R lat equals dmx lat over dt, where R lat is the transition rate from latent to growing cells, and mx lat the mass of latent cells. Introducing the medium volume V and the specific latency constant K lat, the balance relation becomes minus K lat x lat V equals V dx lat over dt. Accordingly, the differential equation describing the time variation of the latent cell concentration is dx lat over dt equals minus K lat x lat. For the growing cells that are produced both by transition from latent cells and by growth, and disappear by the transition to producing cells, the instantaneous balance, in gram cells per hour, on the fermenter writes R lat plus Rx minus RGP equals dmxg over dt, where Rx is the cell's growth rate and mxg the mass of growing cells. Introducing the medium volume V and the specific growth rate mu, the balance relation becomes K lat x lat V plus mu xgv minus kgp xgv equals V dxg over dt. Thus, the differential equation describing the time variation of the growing cell's concentration is dxg over dt equals K lat x lat plus mu xg minus kgp xg. For the producing cells that are produced by transition from growing cells, the instantaneous balance in gram cells per hour on the fermenter writes RGP equals dmxp over dt, where RGP is the transition rate and mxp the mass of producing cells. Introducing the medium volume V and the specific kgp transition rate constant, the balance relation becomes kgp xgpv equals V dxp over dt. Thus, the differential equation describing the time variation of the producing cell's concentration is dxp over dt equals kgp xg. For the produced metabolite, the instantaneous balance in gram metabolite per hour on the fermenter is Rm equals dmm over dt. Rm is the metabolite production rate, and mm the metabolite mass. Introducing the specific metabolite production rate Qm, the balance becomes Qmxp V equals V dm over dt. Accordingly, the differential equation describing the time variation of the metabolite concentration is dm over dt equals Qmxp. For the consumed sugar, the instantaneous balance in gram sugar per hour is minus Rs equals dms over dt. Rs is the sugar consumption rate in the fermenter, and ms the sugar mass. Sugar is consumed by both the growing and producing cells. Introducing the specific sugar consumption rate, QSG, by the growing cells, and the specific sugar consumption rate, QSP, by the producing cells, the balance becomes minus QSG, XG, V, minus QSP, XP, V, equals V ds over dt. And the differential equation describing the time variation of the sugar concentration is ds over dt equals minus QSG, XG, minus QSP, XP. The oxygen balance is more complex than the previous batch mass balances because oxygen is continuously supplied to the fermentation through aeration. To determine the time-dependent variation of the dissolved oxygen concentration, the oxygen balance is formulated for the liquid phase within the fermenter. The instantaneous oxygen balance on the liquid medium phase considers that oxygen is continuously transferred at the rate JO2 from the air and consumed at the rate RO2 in the liquid phase. The instantaneous oxygen balance over the liquid phase in gram oxygen per hour is JO2 minus RO2 equals dMO2 over dt. Due to the low oxygen solubility, the variation rate term, dMO2 over dt, is negligible, and the oxygen balance simplifies to JO2 equals RO2. Thus, at any given moment during fermentation, a quasi-steady state is established in the liquid medium. The oxygen transfer rate, JO2, matches the cellular oxygen consumption rate, RO2. The oxygen transfer rate, JO2, is expressed by its kinetic law, KLA, O2 star minus O2L, V. Introducing the specific oxygen consumption rate, QO2G, by the growing cells, and the specific oxygen consumption rate, QO2P, by the producing cells, the balance becomes KLA, O2 star minus O2L, V equals QO2G, XG, V plus QO2P, XP, V. Reorganizing gives the relation for the dissolved oxygen concentration, O2L equals O2 star minus QO2GXG plus QO2PXP divided by KLA. In summary, the instantaneous mass balances of the components within the fermenter yield the relationships that describe the fermentation dynamics during a batch process. These consist of differential equations for the substrate, biomass, and metabolite concentrations, along with an algebraic equation for the dissolved oxygen concentration. They express the concentrations variations as a function of the specific rates of the used microbial cell. In the final step, the cellular kinetic laws and the oxygen transfer relationships describing the fermentation aeration conditions are combined with the mass balance equations. This results in a system of differential and algebraic equations that governs the time-dependent variations in the concentrations of the fermentation components. To obtain the fermentation dynamics, this system is numerically solved, for instance, using a spreadsheet-based integration solver. The overall modeling methodology is briefly outlined below. Most of the model equations are differential equations that are integrated using a numerical method. The numerical integration approximates the actual solution curve by a polygonal curve made of successive points and straight-line segments. Let's consider the general differential equation describing the time variation of the concentration dC over dt equals a function of c and t. The differential equation is transformed into a finite difference equation by dividing the timescale t into incremental time steps of length delta t. The derivative dC over dt is then approximated by the ratio of the concentration variation delta C to the time step delta T, and the differential equation then becomes delta C over delta T equals A, or delta C equals A delta T. The incremental concentration variation delta C is the difference between the concentration C, T plus delta T, at time T plus delta T, and Ct at time t. The resulting finite difference equation is C t plus delta t equals Ct plus At delta t. At is the slope at time t of the concentration time variation. The difference relation between the concentrations at time t and t plus delta t is used in the following way to carry out the numerical integration. The integration is started from the initial concentration C0. The slope A0 is calculated at time 0, and the concentration C1 at the following time T1 is determined by adding to C0 the concentration increment A0 delta T. At time T1, the slope A1 is then recalculated, and the concentration C2 at the following time T2 is determined as C1 plus A1 delta T. The procedure is repeated to calculate C3 and the following concentrations over the whole investigated time period. In parallel with the numerical integration of the differential equations, a final and essential task is the evaluation of the parameters used in the thermodynamic and kinetic laws of the model. How are these parameter values determined? Some parameters can be obtained from databases or from previous kinetic studies of the fermentation. The remaining unknown parameters are then identified by fitting the simulation results to experimental data, ensuring the best possible agreement between the model predictions and observed fermentation behavior. With the model parameters properly identified, solving the system of equations yields the simulation curves that describe the fermentation dynamics. For the case of glutamic acid fermentation, the simulated profiles accurately reproduce the experimental time courses of sugar, dissolved oxygen, biomass, and glutamate concentrations during the batch process. The model successfully captures the initial lag phase, the rapid growth phase, and, following the temperature shift, the cessation of cell growth, accompanied by a progressive increase in glutamate concentration. It also correctly predicts the steady decrease in sugar concentration and the characteristic pattern of dissolved oxygen, which drops during rapid growth and rises again during the production phase. An additional advantage of the developed physiologically based model is its ability to describe the time-dependent variations of the cellular specific rates during fermentation. In the case of glutamic acid fermentation, the specific growth rate and substrate uptake rate are low during the initial lag phase. They reach their maximum values during the rapid growth phase. The specific metabolite production rate increases sharply following the temperature shift. Subsequently, all rates gradually decline as nutrients become depleted and inhibitory metabolites accumulate. In this tutorial, you learn the methodology for constructing a simulation model of a microbial fermentation based on an analysis of the governing physical and biological phenomena. The main steps include selecting the kinetic laws that characterize the growth and metabolism of the microbial strain used, applying the thermodynamic and kinetic principles that describe oxygen solubility and transfer, deriving the model equations from mass balance relationships for the key fermentation components, solving the resulting system of equations to simulate the time-dependent fermentation dynamics. If interested, you can gain a deeper insight in fermentation simulation models by enrolling in the online courses, Simulation, Scale-Up, and Optimization of Microbial Fermentations, and Digital Scale-Up and Optimization of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.